Okay, good morning everyone. Let's get started with lecture 2 of BMS 300. So today we'll be talking all about water. And as usual, here's an overview of what I will be discussing. So we're going to start our discussion by talking about the structure of water. And we'll see how it's got 3 atoms in a single water molecule, and we'll see how those atoms are held together. The 2 hydrogen atoms and the oxygen atom, they're held together by covalent bonds, and that will lead us to this concept of a dipole moment. So once we understand how a single water molecule is held together, we can see how different water molecules will interact with each other. And depending on how water molecules interact with each other, they can also affect the surrounding substances which interact with them. And that will lead us to 3 types of interactions with water. You can have either hydrophilic interactions, which is water-loving interaction, hydrophobic interaction, which is water-hating interaction, and finally amphipathic interactions, where certain substances have regions which are hydrophobic and other substances which are hydrophilic. Now these 3 concepts of hydrophobic, hydrophilic, and amphipathic interactions will play a very important role in how the cell is organized. It will play a role in the cell membrane. It will have an impact on protein structures. But rather than getting into that in today's lecture, we will do that in tomorrow's lecture. Today we will talk about certain properties of water which can be influenced because of this hydrogen bonding. And so in that regard, we'll talk about what is surface tension, and we'll also discuss about the freezing and the boiling point of water, and what happens to individual water molecules when the water is being boiled or frozen. And it is my hope that as we talk about these properties of water, some of the everyday applications, like whether it is watching water striders walk on the water, or when you're boiling water to make a cup of tea or coffee, or even on a hot day when you see the ice floating on the water, it will all make sense to you. Right? And after that, we'll discuss the concepts of diffusion, which is very essential in biology. We'll talk about osmosis, which can happen across a semi-permeable membrane, and we'll wrap up with how diffusion can lead to an equilibrium being reached. Right? So that is the overview of today's topics, and let's jump into the main constituent of cells. So when you think about a cell, the main component in that cell is water. And so it is important to appreciate that all of the cellular functions, various reactions, they're going to take place in an aqueous environment. And so it is very important to understand the structure of water before we can start appreciating how these different cellular reactions take place. Okay, so with that, let's look at the structure of water. We see that every water molecule is made up of 3 atoms, there are two hydrogen atoms shown here in the yellow circles, and then there is the oxygen atom shown here as the big orange circle. So in order to understand how these three atoms interact with each other, we need to see the structure of the oxygen atom and the structure of the hydrogen atoms. So let's start by looking at the structure of an oxygen atom. Notice that right in the middle there is a nucleus which is positively charged, and it is surrounded by a negatively charged electron cloud. But for the sake of simplicity, what we are doing is we are looking at a two-dimensional representation where these electrons are shown in these shells, which are shown in a two-dimensional representation. So notice here that the nucleus is made up of positively charged protons, and these positive charges they are not repelling each other and the nucleus falling apart because there are these neutrons which have no charge, and they will apply a strong nuclear force, and that is the reason why this nucleus is held together. Now notice that the electrons in the first shell, there are only 2 electrons, and in the second shell, which is the outermost shell, and it is known as the valence shell, and the electrons in this valence shell, they are known as valence electrons. So there are 2 in this innermost shell and 6 in the outermost shell. And in order for the oxygen atom to be in its stable configuration, there needs to be 8 electrons. And so these additional 2 electrons, they are going to be shared by the hydrogen atoms, and that brings us to the structure of the hydrogen atom. So when you compare the structure of the hydrogen atom versus the oxygen atom, the first difference you notice that the hydrogen atom is much smaller, and it makes sense that it has fewer electrons. And notice that every hydrogen atom has only 1 electron, as shown here. And so in order to reach the stable configuration of the oxygen atom, there have to be 2 electrons which are shared from 2 hydrogen atoms. And notice that as these hydrogen atoms share the electrons, that leads to what is known as a covalent bond. So a covalent bond is a chemical linkage formed by the sharing of electrons. So is this all covered in your prerequisite courses? Right, great. So as these electrons are being shared, we will encounter another concept known as the dipole moment. And to understand dipole moment, which is basically the separation of charges, we need to appreciate that the oxygen atoms tend to be more electronegative, and because it is more electronegative, the electrons will spend more time around the oxygen atom in comparison to the hydrogen atom. And because electrons spend more time around the oxygen atom, there is a partial negative charge around the oxygen atom, while there is a partial positive charge around the hydrogen atoms. And the partial positive and negative charges, they are denoted by this delta plus and the delta minus. And so dipole moment is referring to the separation of charges, and it's dependent on 2 things. The first one is the magnitude of the charges, and secondly, it's the distance between those charges. So both distance and magnitude is what is influencing the dipole moment. Now keep in mind that the dipole moment of water is quite large, and because of this dipole moment, we see that hydrogen bonding can occur between the different water molecules. So what is hydrogen bonding? So I've written the definition here. Hydrogen bonding is said to occur when there is an electrostatic attraction between the hydrogen atom in one polar molecule, such as water, and the electronegative atom in a neighboring molecule. So notice here that at any given point in time, a single water molecule can interact with 4 other neighboring water molecules, and with all of these 4 water molecules, there will be hydrogen bonds formed. So just take a look here. The 2 hydrogen atoms in this central water molecule, they're interacting with 2 partially negatively charged oxygen atoms of the neighboring water molecule. And notice here that this oxygen of the central water molecule is interacting with the partial positive charges of the neighboring hydrogen atoms. Alright, so at any given point, a single water molecule can interact with 4 others. Now, the lifetime of these hydrogen bonds is going to be very short. So it's around 10 picoseconds, and so there will be these hydrogen bonds being formed repeatedly, and a single water molecule won't remain bound to the neighboring 4, but that the pairs will keep changing. Right? So based on whether or not different substances can form these hydrogen bonds when they are put in water, there can be 3 types of interactions. Okay, and the first of these types of interaction is the hydrophilic interaction, or the water-loving interaction. The second is hydrophobic interactions, and thirdly we have amphipathic interactions. So we see that hydrophilic interactions can happen whenever these substances can form the hydrogen bonds with the water molecules. And what can form these hydrogen bonds are either charged or polar molecules. We will look at specific examples of charged and polar molecules. And secondly, we see that if you have uncharged or non-polar molecules, they cannot form those hydrogen bonds, and as a result, water cannot act as a solvent for those compounds. And thirdly, you have amphipathic interaction when certain substances have a hydrophobic and a hydrophilic region. So now let's take a look at specific examples of what are these polar and charged molecules. So we will start by looking at the example of sodium chloride. Here's a schematic representation of a cartoon of a sodium chloride crystal. Notice that the sodium ions have a positive charge and chloride has a negative charge. And if you were to take this sodium chloride crystal and put it in a cup of water, this sodium chloride is going to completely dissociate into sodium ions and chloride ions. And the reason it's going to dissociate is because there will be a hydration shell formed around the sodium ions. So notice that the positive charge of the sodium ions can interact with the partial negative charge of the oxygen atoms in the surrounding water molecules. So because of this electrostatic attraction, there's this shell of hydration being formed around sodium. And similarly, you see that even the chloride ions have this hydration shell because the negative charge is going to interact with the partial positive charge of the hydrogen atoms in the surrounding water molecules. So this is just highlighting the hydration shell around both the sodium ions and the chloride ions. So this is the first example of hydrophilic interactions when a given substance is charged. So what is the case in the type of when there is a polar substance? And the example for this is sucrose. Notice here that I've represented the sucrose molecule as a ball and stick model, and let me explain what these different colored circles are referring to. So this white circle is referring to a hydrogen atom, and it's got a positive charge on it, and the red is referring to an oxygen atom, and has a partial negative charge on it. And you can understand why this is the case, because oxygen tends to be more electronegative, and so the electrons spend more time around it. And the black circles denote carbon atoms. So if you were to take a chunk of sucrose and you drop it into a beaker of water, the attraction or the electrostatic attraction holding these sucrose molecules is going to be disrupted because the water will try to form hydrogen bonds with the partial positive and the negative charges in the sucrose molecule. And because those hydrogen bonds are going to form, it will disrupt the electrostatic attraction. And notice that the difference between polar and non-polar polar and charged substances interacting with water is that this polar substance is going to break into smaller pieces of the same molecule. Like sucrose is not going to fall apart, but there will be smaller molecules of sucrose which are pulled apart by these hydrogen bonds. And notice that they are not breaking up into ions like you noticed in sodium chloride. Is that clear? So that is the main difference between polar substances and charged substances when they interact with water. Any questions at all? Should we review? Okay. If there are no questions, we'll move on to hydrophobic interactions. And when you think about hydrophobic, oh yes, you have a question.
I was going to ask for clarification on why sucrose responds which include work that sodium chlorides are not.
Okay, so the question was why is sucrose not falling apart, but only you have the sodium chloride falling apart, right? Ionizing. So the reason for that is that sodium chloride will dissociate into sodium ions and chloride ions because a hydration shell is going to be formed around sodium and chloride. Whereas in the case of the sucrose molecule, a hydration shell is not formed around the individual atoms, rather it is only formed around the entire molecule. And the reason for that is the partial negative charge here of oxygen can interact with the partial positive charge of hydrogen in the water molecule. And similarly, the partial positive charge will interact with the partial negative charge of the water molecules. Yeah, so that's a difference. And also keep in mind that sucrose is made up of multiple atoms, whereas sodium is its own atom and chloride is a different atom as well. Good question. Anything else? Okay, so moving on to hydrophobic interactions. The real life example you can think about is salad dressing. So let's say you take vinegar and you mix it with olive oil and you shake it up and you pour it over the salad. And if you were to keep this aside on the table for a while, you'll notice that the oil is going to rise to the surface. And the reason why the oil rises to the surface is because the atoms in that fat, they are all sharing their electrons equally, and so there is no free charge. If you consider the previous case, I said that oxygen was more electronegative, but in this case, the electrons are being shared equally, and so that is why there is no free charge available. So to better understand why the electrons are being shared equally, we need to take a closer look at the structure of triglycerides. So the term triglycerides, lipids, and fats will be used interchangeably, right? So just a disclaimer so that you know if I'm referring to one, I could be referring to the others also. So if you look at the structure of triglycerides, it's made up of this glycerol backbone, and glycerol is a 3-carbon alcohol. So notice here there's carbon number 1, 2, and 3, and each of these carbons are linked to the alcoholic OH group. Now each of these carbons will be connected to a fatty acid chain, and this is what a single fatty acid chain looks like. Notice that there are a number of carbons which are linked one to another, and at one end you have this carboxylic group shown right here. And so the hydrogen from this alcohol group and the OH from the carboxylic group, they are going to interact in a dehydration reaction, as you see here, and so water will be released as a byproduct. So the specific enzymes which are involved in this dehydration reaction is beyond the scope, but I hope you understand that there are 3 carbons and each of them are linked to a fatty acid chain. Now if you look at this triglyceride, you will see that that there is not big charges there. You'll notice that this ketone group C double bond O, oxygen could be more electronegative, and that could be a partial negative charge. But when you consider the size of the entire molecule, these charges, they are not big enough to interact freely with water, and so that is why triglycerides are hydrophobic. The amount of available charge is very minuscule when you compare it to the size of the entire molecule. Is that clear why lipids can't interact with water? Okay. So moving on to amphipathic interactions. notice that there's going to be a polar region and a non-polar region. So there's a region which is hydrophobic shown here and the hydrophilic region. And when you take an amphipathic molecule and you drop it in a beaker of water, you will notice that two things happen. The hydrophilic region will interact with water, whereas the hydrophobic region is going to interact with each other. And so you will have this micelle-like structure formed, right? And because of this selective interaction with water and selective interaction with each other, we will see that amphipathic substances can have a use in our everyday application. For example, let's say your hand is greasy because you worked on your car or maybe at a greasy wheel. I would probably relate with the latter rather than working on my car. I would take it to a mechanic. But if your hand is greasy and you wash it with soap, it's not going to wash it with water, it will not wash off. And the reason is that water cannot form the hydrogen bonds with the grease on your hands. And so when you use a soap, you're using an amphipathic substance. And so these amphipathic molecules can act as a bridge between the grease on your hands and also the water.
So it's kind of like an emulsifier?
Yep. What was the comment there?
It's kind of like an emulsifier.
Exactly. Yeah. The comment was it's kind of like an emulsifier. We will get to that in the digestive system. All right. But yeah, thanks for mentioning that. There is all the things I'm talking about right now. They're going to tie into the other organ systems. Right. So good point. So notice that the grease particle will be interacting with the hydrophobic region in the soap, and also the hydrophilic region is going to be pointing outwards. And so as a result, we'll see that the grease molecule is going to be coated with charged substances because the hydrophilic region is pointing outward. And assume that all of these charges are the same, two things will happen. Firstly, these charged grease particles, they will start repelling each other because like charges repel. And secondly, these charged particles can also interact with water, and that is why when you use soap, it will help to wash off the grease. Is that clear? Okay. Alright, if that is clear, now we're going to switch gears and talk about some of the properties of water which are linked to this concept of hydrogen bonding. So the first property we're going to consider is surface tension. So the technical definition of surface tension is the forces which are acting at the surface of a liquid, which tends to minimize the exposed surface area. Right? So it's the forces acting at the surface of a liquid which tends to minimize the exposed surface area. But rather than using that technical definition, I want to explain surface tension by using this question here. So the question is, why are water molecules at the surface compressed tightly together? And in order to answer this question, we need to consider that in its liquid state, the water molecules, they are in constant random motion, and this constant random motion is because of the kinetic energy of these water molecules. So there is this constant random motion. And notice that I told you that water molecules can form hydrogen bonds with the surrounding water molecules, and those bonds are going to be very short-lived, around 10 picoseconds. And so when you notice under the surface, a given water molecule is going to be pulled apart in all directions to form the hydrogen bonds. So notice that this water molecule can potentially form hydrogen bonds in all 360 degrees with the surrounding water molecules. Now in contrast to that, if you look at a single water molecule on the surface of a liquid, it has got fewer directions in which it can form those hydrogen bonds. It can form those bonds sidewards or downwards, but at the air-water interface, it can't form any hydrogen bonds. And so it's going to be held together in a lattice structure, right? So we see that the hydrogen bonds between the water molecules at the air-water interface is going to form this lattice-like structure, and that is the reason for the high surface tension. So if you are out for a walk after after the rains, you notice that the water droplets are going to hold this spherical shape, and that is because of the surface tension, which is holding it back and minimizing the overall surface area. Another application of this surface tension is seen in why these little insects called water striders can actually walk on water. So these insects, they're around half an inch in length. They got 3 pairs of legs. So notice here's the first pair, second pair, and then the third pair. And at the tips of each of their legs, they have these tiny hair-like projections which can trap water. That, in addition with the high surface tension of water, is why these insects can run on water and can be very good predators. Okay, so that is another application as well. So now what we'll do is a think, pair, share activity. There are 3 parts to this activity, where you think about the question, you turn to your neighbor and you pair up, and then you share what you think the answer could be. All right, and then I will ask you, some of you, to explain what you think will happen, and we'll be seeing what you understood. All right, so what do you think would happen if you take a water strider and you put it in a beaker of soapy water? Right. So I'll give you guys 30 seconds. Turn to your neighbor and share your thoughts. You may know the answer, but your neighbor may not. If you don't know, ask your neighbor if they do. All right, let's take 30 seconds to talk about this. Alright folks, let's bring it in together. What are your thoughts? Do you think anything would happen at all? Anybody? What do you think would happen? Nothing?
It'll drown.
It'll drown? Why?
Because the surface tension will get broken by the soap. That way, instead of actually staying on top of the water through surface tension, it'll just sink through.
Okay, why will the surface tension be affected?
The soap is affecting the water's molecules, so it's kind of pushing everything apart a little.
Okay, excellent. So, how many of you think the water strider will go down? Okay, that's majority of the class. Alright, so that is correct. Thank you for sharing that. So, what is going to happen is the hydrogen bonds between the water molecules is going to be disrupted by this amphipathic substance. So, soap can disrupt that hydrogen bonding, and when that hydrogen bonding is affected, it's going to affect surface tension, and as a result, this poor water strider would drown. Right? So, the whole concept of surface tension, we will be revisiting again when we talk about the respiratory system. I told you a goal of this course is to integrate information. The micelle formation, which you saw on the previous slide, that's going to tie into the digestive system. So just store this at the back of your mind, but we will be revisiting these concepts. Right? So here's another pair shared activity. So what you notice here is that in this column, the element or compound is given. We have nitrogen, oxygen, water, and the corresponding molecular weight, which is sum of their atomic masses, is given. And on the third column, you notice that their boiling point is given as well. So notice here that water has got a much lower molecular weight, but it has a much higher boiling point when you compare with nitrogen or oxygen. Right? So why is that? So here's another opportunity to turn to your neighbors. If you don't know their names, introduce yourselves, and let's discuss this for 30 seconds and we'll bring it back. Alright folks, I think that's winning back. Anybody else? Share, why do you think water's got a much higher boiling point than these other elements? They said yes.
Because the electrostatic attraction between hydrogen and oxygen is a lot stronger than between oxygen and oxygen or nitrogen and nitrogen. So it takes more energy to like break them apart.
Exactly. So the intermolecular attractive forces is much higher in water compared to the intermolecular forces between oxygen atoms and also nitrogen atoms. So that is the correct answer. So what happens when you add soap to water is you're going to break the hydrogen bonds. But also when you're boiling water, as you increase the temperature of the water, we see that this kinetic energy of the water molecules is going to keep increasing until the certain point where the hydrogen bonds are broken. And that is when the water molecules can escape into the air, and that's how you boil water. So the answer is because the intermolecular forces between the water molecules, which is due to hydrogen bonds, is greater than the intermolecular forces between oxygen and nitrogen atoms. So the last thing per share activity is, what do you think happens when water freezes? So we talked about boiling water. Let's go to the other end of the temperature spectrum. What happens when water gets frozen? We see that ice will float on water, and secondly, when water freezes, it can cause water pipes to burst as well. Right? So why do you think frozen water ice is floating on water, and why would frozen pipes burst? So here's another chance to go to your neighbors and discuss this, and we'll get back in the class. So why does ice float on water? Anybody? I'll come back to you later. I will ask you. Yes. Anybody else? Yes.
So when water freezes, it's becoming a solid instead of being a liquid, so it expands in size, so it has a larger volume, the same mass as water.
So water tends to expand when it freezes. Why does it expand as it freezes?
It expands more. It would expand more because of the hydrogen. Since hydrogen is less density than oxygen, the oxygen compress more, but the hydrogen makes it expand a little bit more into the surface area.
Yeah, the interaction between the molecules is going to be slightly different, and also how the molecules are organized will be different as well. So those are two good points. Anybody else? Yes.
The structure of ice is formed, but there's more space in between the molecules than with water because the molecules are much closer together. and an ice still in fixed form, but there's more space in between molecules, so it's less dense.
Thank you. So just to repeat what you mentioned, that the distance between the water molecules is going to be greater when it's in its liquid form versus when it's in the ice form, right? And the more distance between them, there's going to be less density, right? So let's look at these three pictures. So when you look at water in the vapor state, notice that the water molecules, they are highly disorganized, and the distance between each water molecule is very great. Whereas if you look at it in the liquid state, they are still disorganized, but the distance between them is very less. They're all close to each other, forming those hydrogen bonds. But when water is frozen, as you see in this central panel, notice that the hydrogen bonds are going to be pulled into an open crystalline structure, as you see here. And because of this open crystalline structure, there is less density. And so when there's less density of the water molecules, it's going to be lighter and it will float to the surface. And when there's less density and in this open crystalline structure, it's going to expand, and as a result, frozen water pipes will burst. Is that clear, folks? These are real-life examples. So with that, we will move on to talk about the concept of diffusion and equilibrium. So we talked about hydrophilic interactions of charged substances, and so let's add some numbers, to this example. So let's say you take a spoon of sodium chloride and you add it in a beaker of water. We know that the sodium chloride is going to ionize into sodium and chloride ions. But then we see that the sodium and chloride ions, they're not going to stay together, but they're going to start gradually moving apart, because we see that the thermal energy of the water molecules is going to cause them to bounce against this sodium chloride crystal, and we see that these sodium ions and chloride ions will start getting distributed in this beaker. So initially you'll notice that there's a higher sodium chloride concentration in one part of the beaker, but as you give it time, we see that the ions will move from the region of higher concentration down to the region of lower concentration. And this is what diffusion is. When molecules or ions, they move from a region of higher concentration to a lower concentration. Let's say I take a bottle of perfume and I drop it here, and those of you who are closest to me can smell it first, right? But if you give it sufficient time, no matter from where you enter into the room, you would be able to smell the perfume, because diffusion has taken place and the concentration throughout the room of that perfume is going to be the same. Here's another example. Let's say you have a beaker of water and you put a drop of dye in it. We see that diffusion is going to cause the molecules to be spread out completely, and we see that when all the molecules are spread out evenly in the beaker, that's when we said that equilibrium is going to be reached. So we're going to add a few numbers to this previous example. So let's say that the amount of sodium chloride I took was 5.85 grams, and I dissolve it in a liter of water. You see that the molecular weight of the sodium chloride is 58.5 grams, and so that's why the solution will be 100 millimolar concentration. But keep in mind that because the sodium ions and chloride ions completely dissociate, you will have 100 millimoles of sodium ions and 100 millimoles of chloride ions, and the overall concentration will now go up to 200 millimolar. Is this clear? How when you have substances which can ionize, the amount of the concentration is going to double. Is that clear, folks? Okay, so let's talk about osmosis. So let's say you take this sodium chloride solution and you put it on one side of a beaker, and it is separated from the other side by a selectively permeable membrane. And keep in mind that this membrane is permeable only to water. We see that the water is going to move from this region of higher concentration to the sodium chloride solution. And the reason why water concentration is higher in the right side compared to the left side is that the sodium and chloride ions, they're going to displace the place which will be taken by the water molecules. And so there is more water molecules on the right side compared to the left side. And this is what is osmosis, the process of moving water from a region of higher concentration to a lower concentration across a selectively permeable membrane. So we see that as this water moves from the right side to the left side, the water level in the left side is going to keep gradually increasing. And at one point in time, we see that the weight of this water column on the left side is going to offset the osmotic pressure from the right side. And so this is what is known as the hydrostatic pressure. So the weight of the water column, which is going to offset the osmotic pressure, is the hydrostatic pressure. And when this hydrostatic pressure and the osmotic pressure cancel each other out, water will no longer move from the right side to the left side. So is that clear what hydrostatic pressure is and also what is osmosis? Okay, so let's use a semi-permeable membrane which is selectively permeable to sodium and chloride ions, and it's not permeable to water. So when you have sodium chloride ions on one side and you have water on the other side, we see that because of the kinetic energy of the water molecules, we will have these sodium and chloride ions bouncing against this membrane. And randomly we see that those sodium and chloride ions can move from the left side into the right side column. But keep in mind that the probability of a sodium and chloride ion moving from the right to left will be initially greater. So from the left to right will be initially greater because of the higher concentration. But equilibrium is said to be reached when the probability of the sodium and chloride ions moving from left to right is the same as the probability for moving from right to left. Okay, so with that, I'd like to summarize what we've discussed, and then we'll go over the key questions which I hope you can answer at the end of today's lecture. So we talked about the structure of a water molecule, and we see that it's made up of 3 atoms, 2 hydrogen and 1 oxygen, and they are held together by covalent bonds. But individual water molecules, how they interact with others water molecules is through hydrogen bonding. So a given water molecule is held together by covalent bonds, but how it interacts with other water molecules is through hydrogen bonds. We also see that some substances are hydrophilic if they can form hydrogen bonds with water molecules, and for that we saw the examples are both charged substances and polar substances, and we look at specific examples of each of those. And we see that there are also amphipathic interactions which can disrupt hydrogen bonding, like the example when you use soap on water, that can disrupt the hydrogen bonding, and also heat can cause the hydrogen bonding to be disrupted, and that's why water molecules can escape into the atmosphere when you boil water. And finally, we also talked about the concept of diffusion, where ions or molecules move from a region of higher concentration to a lower concentration, and we see that equilibrium in solution can be reached both by diffusion and osmosis. And osmosis is where water molecules move from a region of higher concentration to a lower concentration across a selectively permeable membrane. Okay, so that was the content I hope to cover in today's lecture. Let's look at some of the key questions I hope you can answer. These are pretty straightforward questions, and I just want you to raise your hand and then you can answer this, right? So what attributes in the structure of water make some molecules hydrophobic and others hydrophilic and others amphipathic? So what in water makes the other molecules hydrophobic, hydrophilic, or amphipathic? Yes?
It's dipoles, the positive and negative ends.
Yeah, it's because of the high dipole moment of water, right? And so because the high dipole moment of water, it's got a partially positive charge on one side and partial negative charge on the other side. And as a result, what happens in the case of hydrophobic interactions? Yes?
The other molecule is non-polar, so it won't be able to react with the dipole ends.
It cannot interact with the dipole ends, and it cannot form blank bonds. Hydrogen bonds, excellent. Whereas in the case of hydrophilic interactions, it can form those hydrogen bonds. So amphipathic substances, part of them can form those hydrogen bonds. They will interact with water. Those parts which cannot form those hydrogen bonds, they will interact with each other and protect themselves from the water. Okay, second question. What attributes in the structure of water give a high surface tension? Somebody else. I just like to mix it up. You want to answer this? Okay. Yes.
So on the surface of water, since, well, in the middle of water, like hydrogen bonds are being formed in all different directions, but on the surface it's only being formed in less directions, which from the highest direction.
Perfect. So, at the water-air interface, the hydrogen bonds can be formed only sidewards and downwards, and so that's going to hold the water in a lattice structure at the air-water interface. Whereas, under the surface, it can form those hydrogen bonds in all directions. Okay. And what attributes in the structure of water give it a high boiling point? Yes. We talked about this a few slides ago. Yes.
Its ability to form hydrogen bonds with itself.
Yes.
Itself together.
So hydrogen bonds are quite strong, and so that's why you need a higher kinetic thermal energy to break those hydrogen bonds, and that's why it has a high boiling point. And why does ice float on water, and what causes it to burst? We already talked about this. We can move on. What is the difference between osmosis and diffusion, and how do they influence equilibrium? So, two parts to the question. What is osmosis?
The flow of water through a channel that's only permeable to water.
Wait, did you want to say?
Oh, no, you're fine.
Okay, yes. So, yeah, let's hear it.
It's the flow of water through a channel that only allows water molecules to flow through while keeping any other molecules on the other side.
Correct. So osmosis is the movement of water from the region of higher to a lower concentration from across a selectively permeable membrane. And what is diffusion? Is it just water, or is it something else? Yes.
So molecules move from a higher concentration to a lower concentration?
Yes. Molecules moving from higher to lower concentration is diffusion. It can happen in the air. It can happen in water. So it can just be ions moving from higher to lower concentration. And how do they influence equilibrium? Yes.
Equilibrium is when the movement from one area to the other is the same.
Yes.
So the concentration of osmosis, if one side has some different molecule in it, if the concentration of water is maxed out, then it'll be equilibrium because the water from the higher concentration to lower concentration is the same.
Excellent. So, to briefly say what you told, when that concentration difference is gone, equilibrium is reached, because on both sides across the membrane, there's the same probability of the ions moving from one side to the other, or water molecules moving from one side to the other, right? Because the concentration difference has been gotten rid of. Okay, and then based on whether a solute dissociates in water, how will it affect the overall concentration of the solution? Will the concentration increase, decrease, or remain same? So there are three options: increase, decrease, remain same. Yes?
The solute dissociating with water doubles the amount of solute.
So the answer is it'll increase it. If it can dissociate, it's going to increase the solute concentration. But if it doesn't dissociate, then it won't increase the solute concentration. Alright folks, we got 2 minutes and we're going to do one hole everywhere question. Alright, so here's the question. You have a beaker with two solutions. On the left side you have 15 millimolar of sodium chloride. On the right side you have 30 millimolar of urea, separated by a membrane that is permeable only to water. Alright, which of the following can occur? Will it be A, B, or C? Okay, let me activate the activity here. And I get to test out whether my updated poll everywhere works or not. Do you think water will flow from left to right or from right to left? And if you don't know the answer, please acknowledge that, because that will give me a sense of where the class is. Or do you think water will not flow? All right, great. We have this. So that means my polar viewer is working great. So that's part of the reason why I put the question today. Okay. All right. So only one person said they don't know. All right. Let's help that one person, and let's help the 45 and the 32. That is how many? Like 77 of you to know that the right answer is actually A. Water will not flow. And let me explain why. So here is 15 millimolar of sodium chloride, and you have 30 millimolar of urea. What I did not mention in the question, which I did mention in the lecture, is that urea is a charged molecule that does not dissociate, just like how sucrose will not. And so, but 15 millimolar of sodium chloride completely dissociates, and so the concentration on the left side is 30 millimolar, matching the urea concentration on the right side, and so water will not flow because osmotic force is not analyzed. Right? So with that, thank you all for your time, and we will do poll everywhere questions related to this topic in tomorrow's class.